All right, so let's start.
Okay, I should be able just to present it in fashion.
Yeah. Yep. Okay, can I get your attention? We're getting ready to start. So this week, our talk is going to be given by Dr. Talent here. Dr. Talent, he has been an adjunct here at UH Clear Lake for a long time. And this year, he's also a visiting assistant professor. And as many of you know, his background is in astronomy, and he's been doing a lot of work in space debris for the last several years. So he's going to be talking a little bit about the 2007 Chinese ASAT test and the implications for that on our low Earth orbit environment. And quickly, next week's talk is going to be by Dan Fry, who is also another adjunct here. And he's going to be talking about dealing with rare and extreme space weather events. So, Dr. Talent?
Thank you. Thank you very much. Sorry to get off to a little bit of a late start. I've been behind my time all day. I have been working in the area of orbital debris since 1986. I was an assistant professor of physics at Abilene Christian University after I finished my my graduate work at Rice University and a 2-year postdoc at Yerkes Observatory, University of Chicago. Thought I would just be a professor and wander around in ill-fitting clothes and spill coffee and dream. But it turns out that my family grew suddenly, and I had to actually, punch out for industry. And I came to work for Lockheed Martin in 1986, and became very much involved in the orbital debris work there. I've been involved in observation with optical systems, CCD cameras on telescopes and things. Been involved in radar data, mostly from the analysis perspective, not from the perspective of actually running those systems. Been involved in theoretical work, which we'll touch on this evening. And I even was involved in a clandestine operation once upon a time, but we won't talk about that. Space debris spy stuff, but it's kind of cool. Okay, in 2007, the Chinese conducted an anti-satellite test, and they really trashed out space in the process. And I have done some analysis of that event, and specifically how long we can anticipate the space trash will stay there in place. And I have done that evaluation in the context of a model, which has gone through several developments of several periods of development, called the particle in box model, which I published in 1992 in the Journal of Spacecraft and Rockets, and then later used that information from the publication to develop a more sophisticated model under an SBIR Phase 1 and 2 grant set, and that is what I used to do some of this analysis. I can give you the heads up on it pretty much right now. By doing this particular event in January of 2007, the Chinese made a real mess of outer space. But there's going to be some steps along the way. Now, you'll see the logo on the bottom here, Oceanit. It's a company I worked for. It's the company I worked for at the time I developed this. So credit to where it's due. I guess I better not just claim I did it on myself without any backing. We actually had funds from SBIR Phase 1 stuff. We developed this particular model called PODEM, Phenomenological Orbital Debris Model. The objectives here is to describe the PODEM model, to present the possibility that it might be a reasonable model. I validated the usefulness of the model against a historic anti-satellite test, the 1985 SolWind test that the United States conducted. We were much more responsible. We blew our stuff up at a low altitude. It all came down quickly. The Chinese government blew their stuff up at a high altitude, and it'll be there for a long, long time. The idea here also is to examine the long-term impact of the Fenyang 1C ASAT test on the LEO environment. And most importantly, I'm using that as a prototype to examine two contrasting space warfare scenarios based on multiple Fenyang 1C equivalent events, as I call them. And for starters, we're going to take a look at the PIB model, which is the forerunner to POTEM, upon which this work is based. In 1988, I set out to develop a model based on a simple differential equation with an approach to the environment that was thermodynamic in character. A peer-reviewed paper was published in 1992, and for the sake of continuity as it relates to the rest of this discussion, I'm going to give you a little bit of background here. Let me tell you, first of all, why I even bothered to develop this model. Real quick, kind of in a nutshell. In 1988, I had been working for Lockheed Martin at the Johnson Space Center for 2 years. I was involved with the orbital debris group. In particular, I was supporting some people like a fellow named Don Kessler, oftentimes recognized as the father of orbital debris, who published the introduction to orbital debris in 1978. He and a fellow named Burton Kerpele. And in 1988, I was with a group that went to the Pentagon. We went to the SDIO Survivability Office, Strategic Defense Initiative, Star Wars, Ronald Reagan's idea, or at least not his idea, he supported it. And one of the things we were there to talk about is what would happen to the space environment if some of the Star Wars scenarios were ever to be played out. We went, it was my first trip to the Pentagon. It was kind of interesting. We walked through the gates. They checked us all out. They had a guard in front, a guard in back, and we all walked like little ducklings down the hallway to a conference room. And we were told, oh, by the way, if we had to get up at any point, we'd have to have an escort to go to the hall, out in the hall. And if we needed to go to the restroom, we had to ask permission. And we had to have an escort to the restroom and the whole 9 yards, because we were not regular employees, we were visitors, and they just didn't seem to like us very much. So in the context of the presentation, some of the senior members of our group with NASA were talking about the possibilities that Star Wars scenarios of various types might lead to a tremendous amount of space trash, and that it might not be such a good idea. I was sitting in the back of the room. I was just a contractor supporting the effort, so I'm sitting in the back of the room, and I'm sitting next to a major, the fellow who was our host, and he leaned over and he said, I don't like what that man is saying. I don't like the model he's basing this on. I don't like him, and I don't think I like you. I said, I'm sorry. I try to be likable. What is your problem? And he said, I'll tell you during the break. So in the break, we were having coffee. He pulled me over to one side and he said, I'll tell you what's wrong with this model they're using. It's thousands of lines long. As it has been described to me, it has not been well documented. It has not been consistently documented. And some of the people who developed it no longer even work at JSC in a capacity as a contractor or civil servant. How do I know there's not one or two lines buried in some subroutine somewhere that's pushing all the solutions in one direction? And this is totally invalid. He said, you're talking to us about making significant changes to our program based on projections that I don't believe. I said, well, what would help you believe? He said, if somebody could come up with a 200 or 300 line program with some basically good physics in it that approaches this a different way, but is totally transparent so I can inspect it, and if that effort would support what this is saying, I might believe it a little bit. I took that as a challenge and went back to my hotel room and sat down and began to construct a model that would be probabilistic in character as opposed to deterministic. The nature of the model that NASA was using was a deterministic program where you had to keep track of all the orbital elements of all of the objects, propagate them forward in time, anticipate the possibilities of collisions under various scenarios. You would have to run the program 50 to 100 times because it used a Monte Carlo technique, And in order to get a single valid statement over a 50 or 100-year period, you take all these runs and average them together. And I decided, what do I need to do to model this environment in a probabilistic way? I thought, well, for starters, I'm going to treat the entire Leo environment as one equivalent box with global average characteristics. And in that box, all the objects will be resident and they can move around. To describe all the objects in the Leo environment in terms of one equivalent particle, whose nature is determined by the total number of objects, cross-sectional area, and mass on orbit at any given time. So basically, I said, let's have some particles in a box, like a shoebox, rattle them around, and see how often collisions take place. And I began to work on that. I thought, okay, what do I need? I need a state parameter. Anytime you do a model, you need some kind of parameter to define the state of the system. In developing a mathematical model of the evolving system, one must first choose a relevant parameter as a state quantity. I decided to choose the number of objects resident in Leo environment at any given time. The reason for that is that if an object can be seen, it can be counted, and the number of objects on orbit is a direct observable, subject to an appreciation of the possibility of incompleteness. As you get to higher altitudes and smaller sizes, it's harder to see the objects. You might miscount, but nothing's perfect. So I ended up describing the basic equation you see here. Now, I didn't just plop it all down all at once. It took me about a half an hour or 45 minutes to come up with it. But it says, okay, n dot, the time rate of change of the number of objects on orbit is equal to a plus bn plus cn squared. The form of the equation is based on this. The first part, A, represents deposition. The deposition rate, the rate at which new objects are put in the Leo environment and which we choose to populate the environment with. The second part is decay due to the atmospheric drag and or random removal. It can be represented as a finite probability per unit time, B, of the decay of any given Leo object. So the number of objects decaying per unit time would be proportional to the product of the probability per unit time times the number of objects on orbit. And the production of new fragments resulting from collision, you don't add any more mass to the environment, but what you do is you add numbers of objects by virtue of the fact that they collide. Why did I use the model I use here? Because if you go to any simple thermodynamic text, or if you can go to something like Haldane-Resnick, Physics 101, 202, whatever, you'll see that when you talk about collisions between the population members of something like a gas, is proportional to the density of the objects on orbit. The simplest model I could think of was n dot equals 0. That's actually the first thing I wrote down. What happens when you integrate n dot equals 0? You get n equals a constant. Now, that's not such a bad model. That's not very useful. In fact, I can go to any one of several websites and I can find the number of objects on orbit today. And it's what's referred to as the box score. And so I take n dot and say it's equal to a constant. I go to the website, I look up the constant, I plug the constant in. I've got a great model. It doesn't predict anything, but it's a reflection of the statement of what is going on today. So it's not very good. So then I said, well, actually, I know it's not with 0. I know we put objects up. Now that's where I put the A in. Well, objects go up, but what goes up must come down most of the time. And that's when I said, well, there is drag. So that's plus B, if there's any sign it's hidden B. And that's the multiple number of objects, N. And then I said, yeah, but there have been cases where objects have collided or suspected to have collided. That's why I got the CN squared. So what I really need to do now here, really more than anything else, is worry about the A, the B, and the C, the coefficients in this equation. Well, where was I going to get those? I decided to get them from the phenomenology. The kind of model I developed here is what I call a phenomenological model. The model structure itself is based on a probabilistic scenario and certain assumptions. The constants that go into the coefficients, I decided to base on real history. The launch term, the deposition coefficient, take A and break it out as this. First of all, there are a number of launches that are done worldwide. I had all the data up to that point in time, and I could look at various publications to project what it was going to be for the near future. So the number of launches. Well, what happens when you launch something? Well, there's a certain number of pieces per launch, P1. I looked at historical data. Typically, whenever we want to launch a payload, we end up putting 3 or 4 pieces of crud up in orbit with it. fairings, shrouds, nuts, bolts, astronaut gloves, Hasselblad cameras, whatever. Out of that number of P1 objects, a fraction of them meet the membership conditions. What are membership conditions? I decided any object that stayed up less than a year, I wasn't going to count it. Wasn't really important enough to be part of the environment. Now, what about the second term in that? Turns out that when we launch stuff, every now and then something blows up in orbit. So I let F sub E be the fraction of launches eventually resulting in an on-orbit non-collisional fragmentation. There have been over 150 of these things. For a while there, Delta II upper stages were popping off periodically, and the Russians had some upper stages that were blowing up. What was happening? We had these individual derelicts. They were easy to track. We knew where they were. They're big hazards to navigation, but we knew they were there. Then, all of a sudden, boom, one of them blows up. Instead of one piece of junk that's easy to track, we had hundreds of pieces of junk that were not so easy to track. Well, that's no good. Why did that happen? In a lot of cases, it was because we would launch something, deploy the payload, forget about the rocket body. It's done its job. Kansas is big. Another beer can out the window doesn't make any difference. Space is big. The Big Sky Theorem, we can just leave our trash laying around. What happened was some of these upper stages had hypergolic fuels. They would have a common bulkhead between the fuel and the oxidizer tank. A lot of these were in orbits where they would heat and cool, heat and cool, heat and cool. Take a wire hanger, bend it this way, bend it this way, bend it this way. After a while, the wire hanger breaks because of metal fatigue. So what happens is this common bulkhead would develop metal fatigue. Eventually it would rupture. What happens when hypergolic fuels get together? They blow up. So boom, we produced all this explosive crap on orbit. Then there's this little term REM. I called this the number of objects removed per year by deliberate retrieval. I mean, there were a few cases of that. For example, LDEF. We left it up there a long time. We went up there, we got it, we brought it back. So I call this removal as a specific mission action. Now, the removal coefficient, the only natural sink is the atmospheric, residual atmosphere at altitude. I took this to be composed of two components, a reduction fraction per year due to natural drag, pretty efficient at 200, 300, 400 kilometers, 500, a little less, 600, a little less, still 700, not much. You get up above that, the atmosphere is thinning out so quickly that you don't get much drag at all, and stuff stays up a very long time. Now, solar cycle does some interesting things. The solar cycle does some really, really interesting stuff in that when we reach solar maximum, the upper atmosphere heats up, expands outward. Density at any given altitude increases, sometimes by as much as 2 orders of magnitude. Objects tend to really plow through this stuff and come down. If you take a look at the number of objects as a function of time, you'll notice it has these little stair steps. And that's because at every solar maximum, we really start sweeping out the lower altitudes. Now, I put in this S term, and the idea of the S term was it would be a dumb sweeper. The thing I thought about was I had to put in a big system that would take down objects proportional to, at some rate, indiscriminate. It would take down all objects, all sizes at the same rate. I called it a dumb sweeper. The thing that was really dumb about it is it would take payloads out just as efficiently as it took junk out. In the particle in box model, its C coefficient is shown here. It's 2 parts. The number of fragments produced per collision minus the 2 destroyed during a collision. That's del. That's the production term. H.11 is the collision frequency between members of a population of identical objects. Remember, in this particular model, I treated all members of the population like identical objects. What I would do is take the total radar cross-section of the entire catalog, and those of you who know anything about radar cross-section know that that's a little suspicious because radar cross-section and physical cross-section are not necessarily the same thing, and for really small sizes, it can get really, really weird, and the correlation can fall apart completely, but that's all I had. So you add up that number, you take the number of objects, divide one by the other, and you get an average particle size. You do the collisions, and with each iteration, you calculate the total number of objects, total amount of area, and you do the division again, and what happens is the size of the average object evolves with the time steps. So here we have H.11. Where do I get that? I get it here. I got this out of out of looking at books like Rife on statistical and thermal physics. And it says there's a fudge factor here. You see that little F sub nu? F stands for fudge. Incomplete mixing factor. Well, see, the equation itself, except for the F part, the equation itself is only really true for objects that have free access to all corners of the box. Now, if you look at a diagram of the Earth with objects orbiting around it, it looks like a bunch of bees buzzing around the hive. It looks pretty random, but the truth of the matter is, any given satellite in orbit is restricted by its inclination, its apogee-perigee. It can't access all parts of the environment. So this F sub nu is what I call an incomplete mixing factor. How do I get that? One way to do it is to calculate it based on all the objects in the catalog, look at the regimes they can occupy, the other objects they can overlap with, and you come up with a incomplete mixing factor that on the average comes out to be around 0.5. Now this has several terms in it. V sub c, the orbital speed at the average population member. Notice multiplied by the square root of 2. That turns out to be like if you're going 7 kilometers per second this way and somebody comes across 7 kilometers per second this way, your speed of impact is about 10 kilometers per second. Turns out that's not too bad. The volume that the thing is in, R sub T top, the radius of the top of the box, R sub B bottom, the bottom of the box, 4/3, the volume in that box, D1 squared, the collisional cross section between the two objects, and the 1 minus 1 over n1 over 2, so that you don't end up counting objects as colliding with themselves, and you carry forward. Now, here's something really, 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 really cool about this whole model. Of course, I think it's cool because I came up with it and I like it. The form of the PIB environmental equation is of simple quadratic. Look at that, quadratic formula. Something you learned in high school. Actually has a real use. H.11 has roots, maybe. Minus b plus or minus square root of b squared minus 4c over 2c. First time I did this publicly, somebody said, you mean 2a? Oh, God, I hope I don't mean 2a, because there's like 200 people in the audience and I look like an idiot. It turns out I switched a couple of the letters around, so this is okay. B minus b plus or minus the square root of b squared minus 4ac over 2a. And what is that? B squared is associated with sinks. AC is associated with sources. The term under the radical is the difference between the sinks and the sources. If the sinks dominate, this thing will have two real roots, and the environment is conditionally stable. I'll tell you more about that in a minute. If it has the two things exactly equal, its Q is equal to 0, and it has one root. The quadratic is a parabola that just touches the x-axis, and it's at the instability threshold. If sinks are less than sources, you're dumping more stuff in than you're pulling out. The environment is unconditionally unstable. Now, without even solving this equation, if you parameterize the equation with these coefficients and you make a good argument for your coefficients, you can use the coefficients themselves to evaluate whether or not the current environment is even stable or not. Now, here's an illustration. I took this case for some reasonable values of the parameters, and I calculated the two roots. Now, what you got here is at a given state, a given step, here's n. This is the actual value of the number of objects on orbit. Now, this plotted here is dn by dt. When dn by dt is positive, the number of objects is tending to increase. When dn by dt is less than 0, when it's negative, the number of objects is tending to decrease. Now, notice where the two roots are, n1 and n2. Let's say the environment is right here at n. Well, what's happening? It's growing. dn by dt is bigger, but it suggests that if this kind of behavior continues, and of course you have to remember that you have to reevaluate this with every step, so the parabola kind of wobbles around and moves up and down. But the thing of it is, if it never gets above n1, what happens is the environment will asymptotically approach n1, and everything's happy. Now, if you have a sudden explosion and you add more objects on orbit, and the number of members of the population get up in here between n1 and n2, Well, you suddenly put a bunch of stuff on, you've made the extra particles, but dN by dt is negative, so boom, the population goes up and it settles back down again. The environment's stable against being pushed over the edge. What if you are right here and you have a horrible event? You produce so much junk that you jump past N2. Look what happens. dN by dt is positive. Environment's going along. Number of objects on orbit starts growing without bound. Well, not really without bound, because in nature what happens is when you start doing that stuff, one object breaks up more objects, they break up more objects, they break up more objects. They start taking all the big pieces, making little pieces out of it, but the little pieces are more strongly coupled to the residual atmosphere. So the sink terms begins to become more important. So what happens is these roots, which got completely blown away and the parabola goes way up in nowhere, after a certain amount of time, the environment will start to self-correct. See, it's chaos. What happens is it will make a chaotic transition to a new stability. But I point out, stable and desirable are not the same thing. What we will find out is that you can produce a situation where the environment will go through a horrible transition and it will become stable again with so many objects in orbit that the average time between collisions becomes commensurate with the mission lifetime of any given object, and that's not any good. What if you built a satellite to function for 5 years, and after about 2.5 years, it gets obliterated? That raises the expense, not to mention puts more trash on orbit. So, big problem. So here's what I did using the nominal numbers that I could come up with based on published resources. I found out that the LEO environment is currently unstable. Right now, the LEO environment is unstable and it is growing. And based on the numbers I plugged in, I find that it will not exhibit two real roots until the year 2410. And the growth could be expected to continue until about 2590 based on the numbers I put in. This also assumes that we just are stupid, that we'll just keep launching junk at the same rate. That, hey, the sky is falling. Don't care. Need to keep launching. Okay, so it's a model. Okay, you do things like that with models. But throughout the growth period, the average object size proceeds to get smaller. Look, see, you're mulching up the environment. All the big stuff's becoming little stuff. But because as it becomes little stuff, the drag term begins to become more important. The sinks begin to dominate sources. The environment turns around, settles down. Look, it's stable again. It's stable, but it's such a high population that it's no longer desirable. That's not good. But one of the things that would be kind of interesting to do, this was a simple model. Single box, single equivalent particle, run the model, here's your results. One of the things that we thought would be interesting when I started to work for Oceanet Laboratories was to take this basic model and advance it. Break the Earth orbital environment up into multiple strata. Break the population up not into one equivalent size, but multiple size bins. So we divided the environment up into 10 strata and 5 size bins. And that introduced collision terms between objects that were of different sizes. I sub j, big object with number 5, big object with number 4, big with number 3, number 2, number 1. And with each of these possible collisions, you get certain numbers of particles produced. Where did I get the models for that? I looked at some of the laboratory cases where they actually took objects and put them in front of hypervelocity guns. And I took historical cases of objects that had been modeled or simulated breakups, try to get a sense of the production parameters. And you see this delta sub ij with k. So what is this? Is a particle of type I with a particle of type j producing a piece of size k. So we end up with this system of coupled differential equations. So the PIB model was extended to an n multistrata system of m species. So you have n by m population equations. In this case, 50 coupled differential equations. And where the coupling terms are in terms of cross-feed terms. For example, when something decays out of one stratum, it decays into another. When an object fragments, it may throw fragments into other strata. When an object suffers collision, the collision fragments may go into other strata. When I launch objects, I don't launch everything into the middle of the environment. I launch it into altitudes that are commensurate with the mission I have in mind. So for reasons that are too complex to go into now, but you can look at my papers and you can look at the stuff and you can challenge it, but you can put your own numbers in. If you don't believe it, you can put your own numbers in. I divided the strata up like this. S1, 350 to 410, S2, 410 to 470, S3, et cetera, et cetera, et cetera. And the strata each get a little larger with each altitude. Why? Because it turns out what I was looking at was the amount of time it took a typical object to drag out through that strata. I played some games, and I characterized the particle types here, T1, T2, T, etc., based on their value of CD A over M. CD, drag coefficient, A over M, area to mass ratio. Okay? You take a big area and a small mass, you have a lot of drag. Okay? It's how parachutes work. If you jump out of an airplane, my flight instructor would have said you were a fool to jump out of a perfectly good airplane. So I never did. My cousin did. Her chute didn't open. She used her reserve. It sort of opened, not completely. Anyway, she hit the pavement at 50 miles an hour. But that's another story. These objects, T1 and T2 objects, represent basically intact satellites and rocket bodies. T3 and T4 represent fragmentation and collision debris, large enough to catalog. How big is big enough to catalog? Basically 10 centimeter diameter and larger end up in the space surveillance catalog. Objects smaller than that, the completeness of the catalog drops off seriously. Between basically 1 centimeter and 10 centimeters, we think there's about 100,000 pieces of untracked but dangerous debris. So we developed this model using $850,000 of taxpayers' money. Thank you. We developed a model called POTEM. We put it in a graphic user interface, and you can sit down and play with this and put in all the different parameters of a given scenario. And in a matter of 30 seconds, you can run 1,000 years. You can't do that in a deterministic model, but of course, we take some shortcuts. Now, here's some POTEM, the baseline case of a LEO environment evolution revisited. I won't read the whole thing here, but this is we took the case that we had and we looked at and noticed that the general features basically come out the same as in the particle in box. For example, comparing the POTEM results to the particle in box results, there's very similar. The primary difference is when the peak occurs, 2590 versus 3000, and their magnitudes, 1.6 million pieces versus 3.4 million pieces. I'm an astronomer. Factors of 2 don't bother me. Okay? We do stuff to orders of magnitude. That's why in astronomy we do everything in the log. Then we take a look over here at the lower right. We can see an interesting behavior. We can actually watch the particles from an explosion or a collision settle down through lower strata. So if you have an event up on a higher level, it'll drift down through the lower level. So if you have a breakup up above space station, you may be okay for now. 20, 30 years from now, when that stuff starts raining down through your level, you may have an enhanced probability of a collision. So is this model any good? Well, what I did is I took historical data. September 13th, 1985, an ASM-135A missile was launched from a modified F-15 at 80,000 feet against the P-78 Sol-Wind satellite, which was a functioning data-gathering satellite. I'm not quite sure why we chose one that was bringing down data. Nonetheless, it produced 285 fragments at 524 kilometers. 11.3 years later, there were only 8 of these fragments still up there. Why? Because we did it in a responsible way at a low enough altitude that most of the stuff dragged out. Now, I ran the model. I used 285 objects at my T3 category, which seemed commensurate with what the data from the catalog was providing. I did the explosion in altitude band S3, which encompassed the actual band that was involved here. A couple of the results, I let my model run for 11.3 years, and I only had 7 objects left. The reality was 8 objects. Okay, maybe I chose, I didn't really try to choose something that was just going to be special. I should look at more cases. But the thing of it is, it seemed to work out pretty well. So, how does this apply to the Chinese ASAT test of January 11th, 2007? We're going to borrow some video here from Satellite Toolkit folks. STK-generated video, courtesy of the Center for Space at this address. I didn't do this. They did. Not my stuff is theirs. It's really good, though. And let's hope that it plays. Please play. I hope we got sound. But I hate to have to sing it. We don't have sound. But it's got music with it. We'll run it again if we have to. But watch. What you're looking at is during the first rev after impact, the Chinese launched a missile from their Zhejiang center, and they hit their target, and they blew it to pieces. Now, some of the fragments received a prograde boost, some received a retrograde retarding impact. What happens is that the stuff that got the prograde boost goes into higher orbits at high apogee, perigee at the breakup altitude. Here we go. Notice what happens because some of the stuff goes higher, it has a longer orbital period, lags behind. Some of the stuff goes lower, shorter orbital period, it comes ahead. From the explosion, population fragments stretch out, forming a ring around the world. Now, because of the altitude differences and the regression of the node of the orbits will now be different over time, the spreading out along the orbit becomes a spreading out around, and basically these fragments will fill up this region of space. Here we see the International Space Station going right through some of this stuff. Do you feel lucky, punk? And then we take a look at the rest of the population. Here's a few other satellites involved. And in a minute, we see the entire population of all objects. Everything in low Earth orbit is now subject to collision concerns because of the Chinese test at a high altitude. So let's take a look at some of the debris characteristics. At January 11th, 2007, 5:28 p.m., they did this. Here you can see a diagram based on actual data where we take the orbital element sets. Orbital element sets are the numbers where it describe the orbit of any given object. From that, you can get apogee and perigee. Take all the objects in the collision. Take a look here. For any given object, you have apogee, perigee, and here's the collision altitude. These objects back here, notice, have an apogee at the altitude of the breakup and a lower perigee. Okay? They were given a kick in such a fashion that they were retrograde, so the perigee drops to a lower altitude. The stuff on the other side, they got the kick in the other direction, so the apogee is a higher altitude. Notice how this is spread throughout the environment. Most of our stuff, most of mankind's stuff is between 300 and 2,000 kilometers, and they managed to put trash in every bit of it. So what I did is I took this thing and I modeled it using using my model, which had been verified against the Sol Wind case, and I am predicting that after 100 years, only 13% of this stuff will have come down. After 500 years, 14% of it will still be left up there. According to the NASA Orbital Debris Program Office, in January of 2008, less than 1% of all the track Phenyon 1C debris had decayed. This I pulled out of an issue, October 2010. You can read the statement over here for yourself. Basically what it says is that in 3.5 years, only 3% of it has come down. There are over 3,037 objects currently cataloged from this breakup. 22% of all space trash is associated with this event. I gave this paper at an international meeting, and there were some representatives there from the Chinese government, and I wasn't very politic about it. I basically said this was really stupid. It turns out that the scientific community in China probably wasn't really behind this. It was the Army flexing its muscles. Well, what could be worse than a single destructive event like Phenyon 1C? The answer would be 20, 50, or 100 equivalent events. Bad news. Well, what if you did it at a low altitude? Space warfare scenario number one. Suppose you blew up 100 F1C equivalent events in the 410 to 470 kilometer range. We went crazy. Everybody else went crazy. We started blowing each other's satellites up. We're very dependent on these satellites. We got people that sit in St. Louis or wherever, Midwest, controlling unmanned aerial vehicles, around the world. How do we do that? We use satellites. We're very dependent on these things for a lot of stuff, for command and control, for intelligence gathering. If this were to happen between 410 and 470, my stratum number 2, take a look. 250,000 pieces of debris. Oh my gosh. Oh well, no big deal. In about 5 years, almost all of it comes down. Now, what happens if you do this at an altitude similar to the Fenyang 1C event itself, between 925 and 1180 kilometers? You have 3 curves here. First curve, the one that peaks in the year 3000, is the case without space warfare engagement. Second curve is the peaks in the year 2900, the case with space warfare engagement. The third line is the difference. The peak is the difference of with minus without. What this means is you put so much trash on orbit, you boost up the collision rate, mulch everything up like crazy, bring it all down. What it means is you can't function. Nobody can function. If we decide to have space warfare with them, whoever we and them are, we will be shooting, they will be shooting ourselves in our collective feet. You cannot do this. Regarding the with case, you notice that it rises faster than the non-warfare case. The peak in population occurs about 100 years sooner, and the value of n being about 500,000 smaller. What happens is the 250,000 pieces during a space war linger in LEO for hundreds of years. Space war debris is responsible for an accelerated rate of collisional breakups. Collisional breakups result in more fragments and so on. The LEO population grinds itself to pieces, and for a long period of time, you can't work in space. Oceanus LEO environment model, I developed it based on the PIB, verified it with the 1985 Solar Wind ASAT test. I predict that in 500 years, 85% of the Fenyang 1C stuff comes down, 15% still up there. The overall implication of all this is even a single significant set of ASAT engagements in LEO could easily result in creating a debris environment that is unacceptable from the perspective of continued normal space operations for all nations. I have had the opportunity to talk to people in various space warfare offices and stuff like that, and in front of audiences at this, and I've basically said the same thing. I can preach it. You can't blow stuff up in space and expect to use the environment. Now, you say, well, I want my space warfare. Well, if you do, don't go blowing up other people's satellites. What you could do is take little bitty satellites, rendezvous with their satellites, and do things like produce a tremendous static discharge that fries the satellite's brains. Another thing you could do is take a little nano satellite that has little tentacles of sticky tape, spin it up, hit the other satellite, the tape wraps around it, messes up the ability to maintain power flow, stuff like that. Great big satellite suddenly just dies. Okay? You don't have to blow things up. Why do people think about doing that? Because, I don't know, it's historical. The military likes to blow stuff up. Even my boys got involved in this. I dedicate this work to my 2 sons, Specialist Aaron Talent, U.S. Army, and Sergeant Byron Talent, U.S. Army, recent veterans of Operation Iraqi Freedom. Aaron is out of the Army and going to school. Byron is currently in Colorado. He's going to be released with a significant medical disability. He didn't get blown up or shot. What happened was he fell off of a tank onto concrete on his back. And now he has problems with his back, so he's going to be out. This is one of the toys that they let him play with when he was over there. And so I thank you very much. Thank you. Any questions? And if you would, speak up, because I forgot to put my hearing aids on. That's the reason I've probably been blowing you all away, because I'm talking loud enough for myself to hear. Yeah.
David, does China not have any significant assets in or use for space, and is that why they even think about messing it up for themselves when they invest in this day?
I have no idea what they were thinking. I've talked to a couple of people who have gone to China, in various exchange formats and political diplomatic things. One fellow in particular, Dave Finkelman, and sat and had lunch with him one day, and he's at CSSI, and I said, I thought, what were the Chinese thinking when they did this? And he said, it wasn't, in his opinion, a decision that was arrived at in a monolithic way, that the people who made the decision really were not cognizant of the degree of problem that they could be causing for everyone. What was really amazing is that this was only a few months after the Chinese government had a representative sign a memorandum of understanding, or not really, it wasn't even that happened. It was kind of a memorandum of goodwill that we would all try to play better in low Earth orbit and not leave so much trash. I think it was some IADC meeting, and they actually had Chinese representatives that signed on to that. And then here, another part of the Chinese government goes and, rather than a saber, blows something up to show if they could do it. What's funny, of course, is less than a year later, we had that thing coming down, and we decided to blow our stuff up too. I think just to show that we could still do it, like we did in '85. It wasn't as bad when we did it, because again, it was low altitude and all that stuff came down pretty quick. Any other questions? Yeah.
What would the material research help you? You think about some material that will minimize the degree. So when it goes up, it will be to pieces that can be easily taken out.
Well, the only thing that I can think of along that line from a material perspective, if you basically take the attitude of, I'm going to put up a satellite that might be a big target, and maybe the responsible thing would be if I get hit, I should at least get hit gracefully, and all pieces should decay. With some kind of stuff that would blossom into big area to mass balloons or something, I'm not really sure how you would do that. Because when you have an impact at near hypervelocity, hypervelocity is truly like 7 kilometers per second and above. This thing distinguishes hypervelocity from a high velocity impact. Hypervelocity is where you actually have shockwave propagation. You get shock melting and stuff going on. In this situation, you have a vehicle that could have an explosive head, or it could just be a kinetic energy vehicle. The thing of it is, if you do it at a high enough altitude, it doesn't make too much difference what the stuff's made out of. You're still going to put that trash on orbit at a high enough altitude that it just isn't going to come down in any reasonable amount of time. Well, another thing that was really interesting about all this is about 2 years before this ASAT test, I was sitting at my desk one day. I was working for Ocean Laboratories, a company based in Hawaii. I was working at home, and all of a sudden my software alerted me that somebody was trying to hack into my machine. I had some software that could trace back the most probable route to the hacker's initial point, and it was at the Harbin Space Institute in China, one of the primary centers for advanced engineering in space systems. And I blocked that place. And about 30 seconds later, I had another attempt to hack into my computer. And I blocked that. And then another, and another, and another. And they were coming from different routes, and all went back to the Harbin Space Institute. And I got on the phone and talked to the security people with the company I worked for at the time. I said, I got something going on. Somebody in China is trying to hack my computer. Unplug your computer. I don't know, it's okay, it's not really hurting me. Unplug your computer. No, it's not like right now they're trying to get it. Unplug your computer. I mean, I had this thing on speaker, my wife says, who's yelling at me? Security. So I unplugged the computer. They had me send in the hard disk, and they did some forensic studies on it, and actually determined that at that particular day, nobody had really gotten anything. And I thought that was interesting. And then it turns out they reported it to the Air Force Office of Scientific Intelligence, the FBI, the CIA, and the NRO. And I ended up with a guy knocking on my door. Yes, hello. Dave Collins here. Who are you? It was really neat. The guy had practiced this. Had this little card. Whoa, hold on a second. What? Stop. FBI. Oh, hey, would you like to come in? Yes, I would. Okay, you come in. We talked about 3 hours about the hacking attempt. We talked about some similar attempts on some other computers in different places. It's kind of a fishing expedition as best as we could figure out. what's really interesting is I was doing a Google on my name, like everybody does Google on their names to see if they're, anywhere important. And I discovered that at the Harvard Institute, there was a whole little research group involved in on-orbit fragmentations, and that my paper, 1992 paper, was actually used as a basis for a couple of leaping off point for a couple of master's thesis equivalent projects in China, and also some work by Don Kessler, by the fellows at a couple of groups in Germany, Italy, and Scotland. They were grabbing a lot of papers on fragmentation phenomena, and then 2 years later, they did this thing. So I don't know if they said, oh, look, it'll make a real mess, and decided to do it, or if the public said, oh, look, it'll make a real mess, but nobody talks to them, and then they make a mess anyway. So anyway, interesting stuff. We should probably try to avoid breaking more stuff up on orbit. The stuff that's already there, can't do much about it. One of the values of this little model, I've taken it around and used it in another mode where I can actually go through all the objects on orbit, take all their element sets, and assess which objects are most likely to suffer the shortest mean time between collisions. These objects are the ones to remove. It turns out that if you take something like 10%, the 10% largest members of the population, that represents something like 80% of the collisional cross-section area. In December of 2009, there was a DARPA meeting on the East Coast, tomorrow I'll link to that, and the general consensus of several groups, not just me, several groups, is that what we really need to do is, we can't do much about the small stuff. It's there, that's the way it is. What we need to do is go after the large derelicts and bring them down. Remove the cross-sectional area for collision, and what happens is instead of doing this big climb and the spike and the unstable, the stable but undesirable thing, you get a nice asymptotic growth to a level that you can deal with. Only bad part about bringing down derelict stuff is somebody's got to pay for it, somebody's got to be responsible for it, and somebody's got to settle those little arguments that are going to come up. Like, I think that rocket body is dangerous. Is it yours? No. It belongs to the Chinese government. I'm going to take it. And maybe I want you to take it because it belongs to them. And so you get into issues like just because something's a piece of trash to you, is it a piece of trash to somebody else? So at this meeting we had in December of 2009, there were a bunch of lawyers. So the net result was nobody got anyway. Anyway, any other questions, comments, or anything like that? Yeah, there and then there. All right, well, sure, okay. And let's go with this gentleman here first, and then I'm here.
What was the method for bringing the large pieces down?
Oh, boy. Well, it turns out that there were about 20 different groups that had papers, and there were about 20 different ideas on how to do that. One of the problems with bringing space trash down that's already up there is nobody thought about it when they put the stuff up there, so it doesn't have any onboard systems, in most cases, to bring the stuff down. So you have to figure out how you're going to go up there, rendezvous with it, grapple it, and then what you're going to do to drop it back into the atmosphere. One possibility is you could, one proposal was, you rendezvous with an object, you attach a payload assist motor and a rudimentary guidance system, nothing too expensive, something you can throw away, orient it the right direction, fire the ripple rocket, and it comes into the atmosphere. Oh, what if I miscalculate? And instead of dropping it in the Atlantic, I drop it on Paris and kill a bunch of people. Well, that's a problem. So there were problems like that. There were some very clever ideas. One idea was where you basically tether yourself to one of these objects, you lower it down using the energy that you are manipulating to raise your orbit to get in position to the next object. You will under with the next object. You use its energy, you lower it down, and you hop around. There was a bunch of different concepts. The Defense Office with DARPA office, they collected all the papers. They published the proceedings. I think they're still thinking about it. But at this point, there has not been anybody settle on a way to do this as far as I know. There are, however, some gentlemen's agreements in place. The IABC, I forget what it stands for, help me, remember? I don't know, somebody, International something debris committee. There are some general understanding, especially in our country, that anything we launch from this point forward, you have to guarantee that it will be down within 25 years. Typical lifetime of most payloads is 3 years, 5 years, 7 years at the outside. And we have to be, anybody that launches something has to guarantee that it will come down in 25 years. I was in a meeting on Friday at the Los Angeles Air Force Base. I actually was out there for a job interview, but they let me sit in on a meeting where they were discussing a Navy payload. Navy wants to put it into orbit. And the Navy said, we can guarantee that this comes down in less than 25 years. And the people at Aerospace Corporation said, we checked their calculations, it's going to be up there 55 years. Well, somebody's doing something. So there was this big fuss that kind of broke out between a certain little group in the Air Force and a certain little group in the Navy. You might wonder why do they have anything to do with each other? It turns out it's an Air Force booster, Navy payload. They've been told to work well and play well together. But the problem of it is the Air Force isn't accepting the Navy's calculations. The Navy says we did our stuff right, we pulled it. And I remember I was sitting in that room listening to people argue about it. And I thought, oh, this is the future. But we actually do, the United States, we try to keep our production of new debris to a minimum, but calculations have been done using my model, the NASA JSC model, the people at Braunschweig in Germany, the Italians, and the Scots. God bless the Scots. All of them have come up with the same thing, that if you stop launching right now, if you stop putting stuff up, the environment is still going to eventually slowly run away, reaching a peak some 1,000 years from now, just because of the large stuff that is currently up there that nobody ever thought of. So the general consensus is, based on all these groups doing all this modeling, is that the world community is going to have to come up with something to remove the large debris. Now, the nice thing about it is, unlike a nuclear runaway, where in picoseconds you go from a bomb to an explosion, this particular runaway takes decades to manifest itself. So it's one of the few things that seems to be commensurate with the time scale of politics. But eventually we will figure out how to, an acceptable way to bring down space trash, and it will be the big stuff that counts to. Anyway, and there was one more question?
Yeah, the solar events actually can reduce some debris. The solar events.
The solar cycle helps a lot, up to about 750 kilometers. As you go above 750 kilometers, the enhancement of density at the peak of the cycle. See, at the solar maximum, you get a lot more UV. A lot more UV heats up the upper atmosphere. Upper atmosphere expands. At a given altitude, you have more drag. Stuff comes down quicker. But at about 750 kilometers and above, it's still happening, but it's such a low density to start with, but even if you enhance it by 2 orders of magnitude, it's still a really low density. It doesn't help very much. There are things we could do. For example, we could put up a launch system, throw away the third stage floating along, and we just have a passive drag system. What we do is we have a canister on the back. The canister opens up, big balloon inflates. Now we have a much bigger area, same amount of mass. Area to mass ratio increases. The object decays and drops into the atmosphere. But then, that's uncontrolled. It could drop in anywhere. The group I was interviewing with out in California, Aerospace Corporation, one of their jobs is to assess the casualty probabilities from re-entering debris. And it's a real sticky wicket. Even if we have, for example, we can keep track of objects in Earth orbit. We watch the orbital element sets. You take the orbital element set on an object at 300 kilometers, and it's orbiting around in a muck, and you'll see the element set change on a weekly basis, and the objects coming in. You might say, how far ahead can you predict? It turns out that you can only predict the data decay to within about 10% of the remaining lifetime. So suppose it's going to be, we figure this object's coming down tomorrow, 24 hours. How good can we predict the actual moment of decay? To within about 2.4 hours. 2.4 hours. That's more than the whole revolution. Oh, good. Somewhere in this 25,000-mile strip, stuff's going to come down. What about one rev ahead? One rev ahead, 90 minutes, 10%, 9 minutes, 9 minutes at 4 miles per second. You still got the width of a continent. It is very hard to predict where stuff's going to come down. The largest object that ever entered was the Mir space station. It entered in a controlled fashion. Back in the 70s, was it Skylab entered? That was really interesting. I don't know how it worked out. I kind of forgot the details of it, but I got a phone call and I was asked if I wanted to go up in a plane with some people from Good Morning America. We went, because it was kind of cloudy, we met at Clover Field at like 3 o'clock in the morning, got on the plane, went up to altitude, and the idea was I was going to do the voiceover as they filmed it, and it turns out they've got this really nice business plane with cross-polarized windows. So when they tried to hang the camera through, all they had to couldn't get the polarizers in the right position. And then the object was at a high angle, and the pilot was trying to maintain this weird 60-degree bank. So I'm saying about this. And we see these Skylab, look at the guy's camera monitor and you see this little dot kind of zoom in, zoom out. We got back to the NASA Johnson Space Center, and in fact, I remember walking across the parking lot, I ran into Alan Bean, and he had been part of this whole group, and I told him what I'd been doing. He said, "Oh, that's really neat. Did you guys get any good footage?" I said, "No, not a thing." But I got to go back in and watch the people do the Good Morning America thing, and they mentioned they didn't get any good footage. But even in that situation, what happened was, I remember when I was looking at it, it was blinking. They're tumbling. They started it tumbling. And I was right. What they did was they were trying to put some degree of spin on it to select the final spot of re-entry. They were trying to get it to enter into the Pacific.
There wasn't a bad button around that to control it.
No, well, it turns out that they didn't really have a good situation maintained. About the best they could do was put a spin on it to kind of increase the average area to mass ratio. Under the circumstances, they thought that would put it down in the South Pacific, and it put like 2/3 of it down in the South Pacific, and the other third of it in Australia. Who cares? That was that. Any other questions, comments? I've taken a lot of your time. Yeah, good.
Actually, I have a piece of Skylar at home.
Oh, how cool.
The tank that came down at carbon composite on the outside, fiberglass station.
Right.
And they cut that out and gave it out as gifts for people who work on Space Station Freedom.
Oh, how really cool. See, someday the space station's going to have to come down.
I just needed a little closure. Did you ever meet the major again? Did he ever start to like you?
No, it turned. I met him at another meeting when I was still working on the program, and I told him that my preliminary results were that he could believe what NASA was telling him. And he just kind of grumbled. I just don't think he liked. He did not like working with civilians, and he didn't like civilians providing data that would impact the program that he had a little piece of, his little fiefdom, and it was really funny. But the net result was, those days came and went, and now we're off to other things. But someday we'll have this issue with the space station. Hopefully, we'll be much more in control of the situation. We'll bring it down gracefully somewhere in the South Pacific. And it'll be something to see. Okay.
Yeah. All right. Thank you.
Thank you.
And this talk will be available online probably as soon as tomorrow. So anybody who, if you missed part of it or you'd like to come back and see this again, just go to our website. It should be posted on there, and you just have to run the WIMBA program in order to get it going.
On the line, huh?
Online.